Hello everyone. Today we will be solving a multi-component flash distillation problem, WANCAT example 2-2. And in this problem we have a stream entering a flash chamber, and we know the composition and flow rate of the stream as well as the temperature and pressure of the drum. And we are tasked with finding out the vapor and liquid flow rates of the outlet streams as well as their compositions. How do we solve a problem like this? Well, the solution strategy for this separation problem, and most of the separation problems that you encounter in this class, is quite straightforward. So the first thing you want to do is you always want to establish the equilibrium relationship. The second thing to do is to conduct a mass balance. Depending on your specific system and specific problem, you may be using different equations to do this, but fundamentally what you need to understand is that in the end, all we're doing is really a mass balance. We're just using different ways of getting to it. The first step is sometimes to conduct an energy balance, and this is optional, and in some problems you won't need to do this, but we're going to add it here for the sake of completeness. The fourth and final step is to determine the number of stages in your system through your mass balance calculations and, if needed, your energy balance calculations. Now, in this specific case, there's only one stage because we only have a single flash tank, but this is useful to keep in mind for future problems. The first part is to calculate the equilibrium relationships. Since this is a multi-component mixture, we're going to be using K values. K values can, of course, be calculated from using a Depreciator chart or the correlations that come from the Depreciator chart. So when we do that, we'll find that K1 is equal to 7. K2 is equal to 2.4. K3 is equal to 0.80. K4 is equal to 0.30. Keep in mind that since the phase transition is happening inside the flash chamber, you're going to have to use the temperature of the flash chamber to calculate your K values and not the temperature of your feed. To do the mass balance, we're going to use the Rockford-Rice equation, which is written as So when this equation is equal to 0, then we know that our VF ratio has converged. Let's do one iteration as an example. Let's guess a value of VF of 0.1. And let's plug that in and see what we get. So the first term is propane. When we sum this up, we get a total value of 0.8785. Now, this is positive, So this means that a higher value of VF is required. So we need to guess a higher value. Once your Rockford-Rice equation has converged, you'll find that your VF ratio will be equal to 0.51. Now that we have the VF ratios, we can calculate the compositions. The liquid compositions can be calculated using this equation. As an example, let's do liquid composition for propane. And when you calculate this, you'll find that this is equal to 0.0739. You can calculate the vapor composition by multiplying Xi with Ki. The flow rates can be found by conducting an overall mass balance. We can just solve for V here. And then the liquid flow rate can be found by just So after you do all the calculations for every component, you'll find that the vapor and liquid compositions will be this, and you'll also have the flow rates. And so this problem is solved. So as you can see,